All right, hello everyone. Welcome to the November 2025 Link Tech Talk. My name is Colin Orion Chandler, and our co-host is Mi Dai. We are both Link Framework project scientists, and I'm at the Rack Institute, University of Washington, and Mi is at University of Pittsburgh. These Link Tech Talks include presentations and demonstrations showcasing work done by the broader Rubin community and archive community as well, with the goal of further enabling LSST science. And unlike traditional tech talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done. So we hope these talks provide a useful forum to discuss a range of groups and authors to present, learning and discussing efforts of interest for analysis of LSST data. Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. And today our speaker is Arkaprabha Ganguli, who's going to present his work, Representation Learning in Scientific Datasets with Disentangled Generative ML Models. Ark is a postdoc at Argonne National Laboratory, specializing in statistical machine learning and its application to nuclear physics. He holds a PhD in statistics from Michigan State, where his research focused on advanced statistical methodologies for feature selection in ultra-high dimensional datasets. Ark's academic background includes a bachelor's and master's in statistics from University of Calcutta in India, and research involves developing and applying statistical methods for analyzing high-dimensional datasets, feature selection, deep learning, generative models. So as we get the talk going, I'm pleased to ask questions in Zoom or in the Tech Talks channel on Discovery Line Slack. On Zoom, you can type in questions in chat or raise your hand. Arka has asked that folks ask questions as they come up, just to make sure that everyone is following what's happening as we go along. And as a friendly reminder, these talks are being recorded and they will be posted on YouTube later. So with that, Arka, please take it away.
Right. Thank you for the very kind introduction and the invitation, Aritra. So I'll just share my screen. Can you all see my slides?
Yeah, looks good. Thanks.
All right. Right. Okay, so I'll start, and I think I'll be done within 40 minutes or so, 40 or 45 minutes. So we'll have some.
Please.
Sorry. Okay, so I think I'll be done by 45 minutes. So we will have some time to like question answer at the end. But as Colin said at the beginning, please feel free to interrupt me and ask question if you need to understand any part within the slides to understand the flow of the presentation. So today I'll be talking about our recent works on disentangled generative models, developing disentangled generative models for scientific applications. And typically for this work, we worked on cosmological or astronomical datasets. I am a trained statistician. I studied and I worked in statistics, but for different scientific applications, I think machine learning and artificial intelligence, these methods are really helpful. From my end, what I like to study is basically how we can utilize the notions of statistics and customize it, use it to customize the existing out-of-the-shelf AI or ML tools to address some of the research question in the domain science. So this work is one typical example of that. We used then some of the statistical notions and implemented it in machine learning methods, generative models, and used it for cosmological datasets. So that's the very high level overview of the talk. This is the our team members. Most of them are from Argonne, and Julie is from National Renewable Energy Lab. I think all of them are basically statistician or applied mathematician, and Nessa and Florian, they are the cosmologics. They are the domain science expert and provided us all the needed information from cosmology or astro side of the science. So with that, I'll begin, and feel free to interrupt me at any point. So my talk is mostly on disentangled generative models, and what we will disentangle is basically the latent space of the generative model. Let's think about the variational autoencoder. So here what we do is basically when we have some data set, for example, some image of the galaxies X, what we will do is basically we we pass it through two different things. The first, we pass it through the latent probabilistic encoder and come to this compressed latent representation of the data, which is represented as Z. And then we will decompress it again using some probabilistic decoder and reconstruct the image as X dash. We will learn that the network parameters in the encoder and decoder by minimizing the distance between the input image and the reconstructed image. That's the overall strategy of variation autoencoder, which is, I think, one of the very primary generative models that people use these days. Right now we have so many other different improvements over variation autoencoder like diffusion, flow matching, etc., etc., etc. I will talk about those methods later in this presentation, but to understand the flow, let me just start with the variation autoencoder. So here we will focus on this latent part Z, which is basically some kind of compressed representation of your high dimensional images, right? So we have this X, which is something like galaxy, but through this, we come to this, from X, we come to this latent space Z, and then we decompress the Z to get the original input space. By that, we learn the underlying likelihood, but at the same time, we also learn this very informative low dimensional manifold of the data. Now, here's come this fact, this disentangled representation. For example, think about some data set where each image is actually coming from some particular configuration of underlying parameters. To understand this, I think this data set of which is basically very commonly used in machine learning literature. This is, I think, DS sprites. This consists of like several different this kind of blobs, but all these blobs are basically kind of characterized or categorized by 4 or 5 generative factors. These are actually mentioned here, like scale, orientation, X position, and Y position. We can see, like, if I change the scale, how the blobs are actually changing. If I change the orientation, how the blobs are changing, something like that. So they have some true ground truth factors. And if I change the ground configuration of those ground truth factors, then the image will be changed. So what we mean by the disentanglement is basically, if we have something of this kind of thing, like if we have some particular property where the images are actually dependent on the latent factors that we have, they should be one-to-one way correlated with those factors. If I change one latent dimension, only one associated ground truth factors will be changing. So that's what we mean by disentanglement. There is interpretability, and the factors are basically one-to-one way correlated with the latent space. And by achieving that, we will have overall control over the underlying likelihood and the generation purpose as well. So people started thinking about this disentanglement idea for a long time. I think Google published one of their main library on disentangled generative models in 2019. But the thing is, like, they are mostly focusing on this kind of toy data sets where they have existing, like, exhaustive knowledge of all the ground truth factors of the images, right? And typically they use two different things, two different approaches. The first one is basically just unsupervised way. Like, they're assuming that there are some ground truth factors are there, like images are coming from some configuration of the ground truth factors. And what they do is basically think about, okay, yeah, think about this latent space that I was showing before. They impose some kind of independent structure over this latent space Z, so that this Z can capture like different independent part of your latent space. That's a great way to do that. And this beta VAE, I think many of you have heard about it. That's actually one way to achieve that. It's like unsupervised. So basically they do not explicitly use any like measured value of this scale, orientation, X position, Y position. They just independent put some kind of independent regularization to get these different kinds of independent structure in the latent space. So that's nice. And the second approach is basically some kind of semi-supervised way where they actually measure each of these ground truth factors and make these latent space Z correlate with one-to-one way with these generative factors. So that's, I would say, that's more like um, semi-supervised way because they are actually utilizing this the measured value of these ground truth factors. So that's what we have so far in the literature. Most of the disentanglement literature is focusing on some kind of computer vision kind of task with toy data. And what I will show next is basically this thing is not exactly applicable for scientific datasets. So for scientific datasets, the idea is a little bit different, right? For example, here what I am talking about, suppose it's something like a galaxy image, and many times for this kind of scientific application, the domain scientist knows some kind of notion of some partially known factors. For example, they know that if I see a galaxy image, we can calculate the mass, radius, and its gravitational shear. So these kind of properties. And we know that these parameters are actually important to know the underlying likelihood of these galaxy distributions. So they have some kind of partially known factors. But at the same time, there is a big unknown set as well. It is not possible to exhaustively know all the possible ground truth factors for this kind of scientific application. For example, galaxy simulation or dark matter, halo structures, and everything. So we have some partial idea. We call it known knowns because we know them, we know that they're important, and we know how to measure them. At the same time, we know that there is a vast amount of ground truth factors are there. They are unknown. We don't know how they're affecting the likelihood, and we don't know how we can measure them. So that's how it's a little bit, this scientific application is a little bit different than this computer science application or this computer vision task that I was showing before. So here we have this kind of discrepancy. We know something and we don't know a lot of things. So what we want in this kind of latent factors is basically they will be restricted enough to align with these known factors like this mass, radius, or gravitational shear. But that's, at the same time, they will be flexible enough to cover all the unknown factors as well. And by doing that, by doing this both thing, we will go back to this and we will learn the underlying whole likelihood for this image distribution, for example, galaxy images, right? So while doing that, we will know what we know and what we don't know, and we kind of measure the discrepancy between these two. So that gives us this overall control or interpretability into these machine learning models. I think that's one of the very big, what should I say, issue for this kind of generative models for scientific applications because they are black box. We cannot interpret them with respect to the ground truth factors. So with this kind of disentanglement approach, one, we can get the interpretability. Second, we can understand what's going on in the underlying likelihood in the light of these known factors that the domain scientist can care about. So that's the strategy, and we developed kind of two different methods for variational autoencoder and flow matching, which can do this kind of disentanglement in the latent space. So that's what I'll talk next. So this is the very brief outline of my talk. I think I already mentioned the first two, why the disentangled latent representation is important for scientific applications. And then um, the first thing I will propose is basically, I'll demonstrate is basically our first approach, which is AUXVA, auxiliary variable informed variation autoencoder. And I'll show its application on this GalSim generated galaxy images. And second, we will show some extension of this approach to flow matching. And we implemented it on this TSZ maps of dark matter halos. And then finally, I concluded with some summary and the discussion. All right. So before I go into the approach, is there any question? All right. Okay. So, okay. So the first thing is the VAE I mentioned that we will develop the disentangled approach in the variation autoencoder framework first. So here, as I mentioned before, we start with the input X, we pass it through the probabilistic encoder, we come to this uh, compressed representation of the data, latent space Z, and then we will decode it back to the original input space X dash. And then we learn this encoder and decoder network parameters by minimizing minimizing the loss between the input image X and the reconstructed image X dash. Now, to get the disentanglement, what we can actually do is basically just divide the latent space into two halves. The first half we call Zox, which will be used to um, which will be highly associated with the underlying this known factors that the domain scientists care about, what they can measure actually. For example, this mass, radius, or gravitational shears. So the Zox will be associated with that and will be completely capturing those known factors. Whereas the Z reconstruction is basically completely independent of the Zox. That means they will be completely independent of this known factors, and they represent all the unknown factors that you have in the data. We don't know them, we cannot measure them, but we know they are there to learn the underlying likelihood. If we just neglect them, it's not possible to recover the underlying likelihood well. So that's why both the things are important, and uh, putting the independent structure between these two is also very important. Otherwise, there will be information leakage. We say that okay, the Zox is highly associated with mass, but then if these two are not independent, then some of the information of the mass or radius will be captured by here, which is not what we want. So we want the proper independent structure between these two. So that's what our basic method, and we call it auxiliary information guided VAE, which is the aux VAE. How we do it? So to understand the method and the data a little bit mathematical structure, let's just call our observed database D, for which we have like different NIID data points. By data point means these X's are the galaxy images that I showed before, and these U's are basically the known auxiliary information like mass, radius, and gravitational shears or something, right? So we have our data in this tuple format. We have X, the image, and the auxiliary information. And that's how we have this n points. Now, in the VAE framework, what we have first is basically the to illustrate the characterization of the disentanglement, we can actually very clearly represent it into these three different characteristics. The first is basically the interdependence. That means the auxiliary information U will be only highly associated with the Zox, the first half of the latent factor. So there will be highly correlation, right? Like this. At the same time, we also need the intradependence. That means like one-to-one thing. U1 will be independent of like Z2. U1 will be only associated with Z1, right? That's the explicitness. So correlation between U1 and Z1 will be 1. That's what we want. At the same time, we want interdependence, which is basically within the group, there will be independence between two different characteristics. For example, U1 will be independent with Z2, Z3, and everything. And the third is basically the interdependence, which is independence between two different groups. Zox and Z reconstruction will be highly independent. And by doing that, U and Z reconstruction will be also independent, right? So the three different structure of the disentanglement can be nicely represented by these three characteristics. And then what we can do is basically now in a Bayesian structure, we can impose simple disentangled prior on the latent space Z. So we have this latent space Z. So what we are doing now is basically we are dividing into these two parts, Zox and Z reconstruction. The first part of the Zox is basically, instead of putting like standard 0 1 standard normal 0 1 prior, which is the common practice in VAE literature. What we do here is basically instead of normal 0 1, we put normal with mean uj, like that known factors with a very like shrinking divergence as like 1 divided by n. So as n goes to infinity, your this normal distribution is becoming singular, and it will converge to this known factors uj, right? So by doing this kind of disentangled prior, what we can actually impose is what we are showing here is like the zj is highly associated with uj, with, and as n goes to infinity, it will just more and more associated with uj. And by doing this kind of independent structure, we are also showing that gj is independent with uj dash for j dash not equal to j. In the second part, for the Z reconstruction part, we don't know anything about it, right? Because it's just covering the unknown information. We don't have any kind of information for this. And that's why we are just imposing standard normal 0 1, because we don't know anything about it and we need to learn it from the data. So that's our very basic first thing, which is basically imposing the disentangled prior to get this kind of disentanglement. If we do it, then we can actually show that the inter and interdependence property can be easily shown, like expectation of uj and zz dash will be expectation of uj and expectation of zz dash, which is like the very standard definition of independence. Secondly, we can also show that as n goes to infinity, the correlation between uj and gj, like u1 g1 u2 z2, this kind of pairwise correlation, they will be go to infinity, they will be go to 1. So they will be exactly 1-to-1 correlation. So we have all these things. And with that, we should actually achieve disentanglement very nicely. But at the same time, as shown in many literature in scientific applications, only focusing on the prior is not enough. We need to somehow put some kind of posterior regularization as well to incorporate or to get this kind of disentanglement effect in your final generative model. So now what we need to do is basically impose this same three properties in the posterior distribution of the Z as well, which is difficult, I think, because now in the prior, when we are talking about the prior, we always use this normal distribution and the closed form solution to get this kind of nice structure of the independence, right? But when you're talking about the posterior, generally the posterior doesn't have nice closed form solution, and there putting this kind of regularization is quite difficult. And as you can see, the conditions are basically mostly to compare or to capture the dependency between two different variables, u and z, right? So we can always use, and that's what we need to do for the posterior regularization as well. We need to make sure that in the posterior distribution also, the z and the u's are maintaining those three properties: interdependence, intradependence, and explicitness. But the point is capturing this kind of dependency structure or dependency strength for two different variable. In general, it's tricky. People used mutual information or this kind of thing for nonlinear dependency, but here we need to actually do it at every batch. So we need a very lightweight metric to capture this dependency in a nonlinear way. And that's where we actually went back to our very own polynomial regression. And what we did to capture to understand the dependency between two variable v and w, we just aggregate the correlation between different polynomial degrees of this v and w, and then aggregate them in this way, right? So penalizing this R naught would reduce the dependency, because it is actually capturing how much correlation is there in this all possible different polynomial degrees of v and w. So we will use it to incorporate this intradependence or interdependence kind of regularization. Second thing is basically we also need the explicitness thing, right? Because explicitness mentions this one, like how u and z ox are highly correlated. So for that, what we did is basically just 1 minus of the correlation, and we impose that restriction in the loss function. So finally, in this setting, our final objective is basically this loss function of the Aux VA. It's nothing but the usual VA loss, but then we have these three different regularization that actually enforce the three characteristic property that I mentioned at the beginning, like the interdependence, and explicitness, using this very lightweight polynomial regression dependent metric, which can very nicely capture the dependency between two variable, but it's not linear. So we have the nonlinear dependency as well here, but it's very lightweight, as unlike the mutual information kind of metric. So that's why we actually used it here. With that, we have our full model ready to train it and learn the underlying likelihood with the disentanglement framework. There are a few more mathematical details as well. I did not mention about that much detail in this talk because it's mostly like its application in cosmology. If anyone is interested, our paper is actually published in Springer Machine Learning. You can just scan it and take a look later and get back to me if you have any kind of question. So now I will show a couple of application results on the cosmology, on the GalSim generated galaxy images application. So for this data, we have around 16,000 galaxy images. And when I call about this known factors, for all of these galaxy images, the domain scientists, they gave us 5 different generative factors like this radius, G1, G2 are like two different gravitational shears, flux and PSF. Typical 5 example of this galaxy images are like this. So that's our data. We want to fit a generative model to learn the underlying likelihood of these galaxy images, but at the same time, we also want to see how these disentanglement effects are and what can they bring to the domain scientist. So first thing that we wanted to check is basically how the reconstructions are, because we are imposing some kind of inductive biases here, and that should not mess with the reconstruction ability of the model, right? So the first thing we need to check is how the reconstruction ability for a given input, what's the output of the VA, and that should be very close enough. So here I am showing, like, in the first row is the input of the VA from a test data, test split, and the second row is basically the output. So we can see, like, mostly they are very similar to each other. We can see a little bit granularity issue here, but overall we see nice agreement between the input and output. Next thing we will check is basically how the disentanglements are. For that, I am showing here 2 different experiments. The first thing is basically the latent space traversal. For this, we fix like different latent factors at a time. And for example, the first one, I only gradually change Z1 from -3 to +3 and keep the Z2 to rest of them fixed as it is, right? By that, I want to see basically how the change in the latent factor are actually affecting the reconstructed images. So here, for the first one, I fix Z2 to Z5 and change Z1 from -3 to +3 and pass it through the decoder to generate it again. I see that for small value of Z1, you can only see, like, the effect is only on the radius, and the G1 is only supposed to capture the radius only. It's free from all the others. So we can see if we gradually increase it, only the radius is changing. Same thing is true for G2 and G3. Like, they are actually capturing the G1 and G2, like 2 different gravitational shears. So if I change them, we can only see that how they are actually stretched and rotated, that thing is actually changing. And for this experiment, I only used radius, G1 and G2 as the 3 partially known auxiliary information. All of them are basically, I didn't use anything else. So all of the remaining factors are basically unknown, and they are captured by the Z reconstruction, the additional latent factors. So this is the first experiment that we did to show that, okay, we achieved the disentanglement. If we change only one latent space, only the corresponding ground truth factors are changing only. That similar thing is basically kind of showed here as the Z versus U scatter plot. Here what I did is for this image, for these plots, in the x-axis, the latent space, latent factors are here like Z1, Z2, Z3, Z4 like this, column wise. And row wise, like the first row is basically the radius, second row G1, third row G2, and so forth. We see that Z1 is only associated with radius, and it's completely independent with four other latent factors, four other ground truth factors. Similar thing, Z2 is only associated with G1, and it's completely independent of rest of them. So that's what we actually wanted to achieve. We wanted to capture this in a one-to-one way. Only one latent factor is associated with the corresponding one, and it's independent of everything else. So it was great, and this experiment actually kind of showed us that in realistic scientific applications, we can also get this kind of proper disentanglement. And now this actually opens a lot of questions, like how the scientists can check uh, how they're fixing the some level of the radius, how they're actually affecting other known factors. They can actually use the VAE to generate samples by restricting those kind of conditions. Like they want to see, suppose I fix the radius in this region, and then I fix the G1, G2 at these two level, and then I want to see what's the actual underlying distribution of the galaxies in this configuration. So using this kind of disentanglement approach, we can actually generate those kind of conditional generation, which is somewhat very interesting from us as a statistician. And we hope that this would be helpful for domain scientists as well. So that's the first experiment that we did for the VAE application. And then the next one, basically, we went to from the galaxy simulation example, we went to the dark matter halo structure generation. And there, these are basically these TSZ maps of the dark matter halos. One thing that we first checked is basically these images are very, very crisp. They are not like the previous galaxy images, which are nice, and those are simulated galaxy images. So they're very nice when well behaved. And that's why probably the VAE worked very well there. But here, the images are so crisp. If I use a VAE, the VAE was not able to capture this underlying, this strong dependency property here. So unless I use some kind of Gaussian blurring filter here to blur the images, and then the VAE can actually learn some of it, but it was not good. So, and when I went back to the literature and I saw that, okay, the standard VAE actually has this problem. It oversmooths this fine structure. It has this blurring effect, and it has this problem in generating very, very crisp images from the data. And that's why people actually these days moved from VAE to more advanced model like diffusion or flow matching. So that's why we went to this. We thought that, okay, the VAE is not working well for this application, so we have to use the something different, which is like either diffusion or flow matching. So this is our next extension of this disentanglement approach to the flow matching models. So for a brief introduction of the flow matching, it's something very similar to diffusion model. Here we start from standard Gaussian distribution, some kind of noise distribution, and then iteratively denoise it again and again and again until we end at the original ground truth images, right? So we basically learned through different denoising steps how to transform a Gaussian noise or an uniform noise to a galaxy image or this kind of halo structure, right? So there, the first point was basically unlike VAE, as you probably can understand here now, that here we actually do not have a very standard latent factor, right? Because it's a like one after another denoising step. What we can call about the latent space here, it's not very trivial. So what we did here is we used a different approach, which is basically latent CFM, latent conditional flow matching. What we did is for each of the denoising step, instead of just carry forward from the previous noise layer to the next denoised step, we actually inject each denoising step by a latent factor. And here we use the similar disentangled latent factor that we used in OXVAE in this framework. Like we start from the image, we pass it through the encoder, we end up at some kind of some latent space Z, and then we enforce this. We divide the Z into half, ZOX and Z reconstruction. We enforce the ZOX to align with the known info, partially known information, and keep the Z reconstruction independent and flexible enough to cover all the unknown information. And then we actually add or infuse this latent space at each of the denoising step. So we make it somewhat disentangled. And that's how we can actually achieve the disentanglement even for the uh, diffusion or flow matching model where we do not have a standard latent factor or latent space for this diffusion or flow matching models. We actually worked on that and worked on this, and this paper recently got accepted at New Deep's ML for Science workshop. We are kind of finalizing the manuscript, and we will submit it soon, the preprint version. So to see how the applications are for this TSZ map, what I did here is like here our two different known factors are this M200C and C200C. These are the mass and concentration of the halo structures. And then similar, if I do the similar latent space traversal, I fix all the latent factors and just change Z1 from -3 to +3. I see that only the mass is actually changing and it's getting bigger and bigger. For example, on the other hand, if I fix everything else, change the latent second factor from a small value to high value, we see that how the concentration is changing. Concentration is actually increasing, right? Similar Z versus U plots are here. You see that Z1 is associated with mass, Z2 is associated with concentration, and everything else is basically kind of somewhat independent. And this last few are basically the Z deconstruction part. We also tried to try to check like how the generated images and the original ground truth halo structures, how they're actually similar to each other. For that, we actually capture different distribution distances. For example, Wassersteiner Sinkhorn, some kind of energy, MMD distance, and everything. And all these things are actually showing this ICFM is basically a very standard flow matching model, which is not disentangled. So these ICFM methods are basically used a lot for just generating new samples. They're very efficient in generating new samples, but they cannot maintain this kind of disentanglement within their framework. So why we compare between ICFM, which is a standard flow matching model, and this disentangled LCFM, which is the disentangled version of the flow matching, is basically to show that we have similar generation ability for a standard CFM model or a disentangled CFM model. So we are not losing in terms of reconstruction or generation, but at the same time, we can actually get this kind of interpretable structure in your latent space, which can tell the domain scientist a lot about the underlying distribution and how the parameters are actually dependent on your distribution, or this kind of story. With that, the third thing was basically very interesting to us. Before going there, Colin, how am I doing with respect to the time? And do I have?
Yeah, you're doing great.
Okay.
How much time? Yeah, I mean, we're at 20 till, so we're going for another 10 minutes or so.
Okay. So yeah, I'll just briefly talk about this one. So here in this plot, what I wanted to show is basically how the conditional distributions are. For that, what I mean is basically, sorry. So here you can see like how the latent factors are, right? Like they are associated, the Z1, Z2, Z3, Z4, Z5. Z1, Z2 are associated with mass and concentration, and Z2 to rest of them are basically kind of independent. They are not much associated with this mass and concentration. What they can actually tell us, all the underlying factors that are outside or independent of this mass and concentration. To understand that, what we did is here, we first fix the Z1, Z2 at some very low, small value. That means we are focusing on low mass and concentration halos. And then I generate 100 samples from this, 100 samples from this centered part of this latent space. That means mode of the latent space, okay? And then we see that, okay, generated samples are very nice, where they're very close enough to the real data, but at the same time, they're also very nicely, what should I say, very relaxed halos. But if I sample from the tail of this latent space, additional latent space, which are actually like independent of the mass and concentration, but gives us the unknown factors, and I am actually generating new samples from this tail of this distribution and then pass it through the flow to generate the according samples, I see that these are the samples from there. So these are coming from the tail, and these are coming from the mode of the distribution. And if I go back and forth between these two, we can clearly see the distribution shift between these two regimes. The central part is always giving us something which is more common in the data. There are not much mergers actually in this data, but when we look into the tail, which are like a less probabilistic region and kind of independent.
Oh, a little bit of a network problem, looks like.
Yeah.
So let's give it a moment here. Oh, we'll just have a little coffee break. Give the speaker a moment to reconnect.
Can you all hear me?
Yep, you're good to
Okay.
go.
Okay. Sorry, I don't know what actually happened. So yeah. Okay. I'll just start quickly from I think where I end, and then I will just jump to the Q&A if there is any question. So at the end, what I was actually saying that we have this different structure that are actually generated from the generative models, but how do we know that they are actually proper samples, right? They are following the physics. In other applications, what they check is basically they follow the actual numerical model or the diffusion the differential equation, the actual OD and PDs, and check if the generated images are a solution for that. But for this kind of cosmological simulation, what my collaborators are actually telling me, that's not a very feasible solution. So we don't actually know any way to understand or properly check if the models are hallucinating or not. I kind of tried to come up with one like quantitative approach. Basically, what I try to do is basically for each generated sample, I run a k nearest neighbor in my training or test data and try to come up, try to find the closest original image, which are actually very nearest to the generated image. That actually shows that okay, the generated image and the nearest original, they are similar enough. So that what we are generating, they are not far from the actual underlying physics. But I would say that this is a very quantitative approach, not very straightforward or not very strong approach to check if the models are hallucinating or not. In other application, they just directly use the underlying OD or PDEs to see if the generated images are solving that equation or not. For us, it's not very trivial. With that, we are actually working on that, and hopefully we can find a little bit more straightforward and better approach to pinpoint on this direction. With that, I'll just finally conclude that we try to develop two different approaches using variational autoencoder and flow matching that gives us this kind of disentangled latent space, which enhance the interpretability of your underlying model, of your underlying data. So it's a tool, and we are reaching out to different domains of different domains of scientists to for this kind of methods, and if they are actually they can implement this kind of generative models, because in many scientific domain, people are actually implementing these different generative models. What we are actually doing here, that's nothing far from that. What we only need on top of your original image space X, or I'm saying image, but it can be any kind of data, any kind of tensor. We on top of that, we just need the additional known factors U. Based on that, we will disentangle our latent space into two hubs. The first part is associated with the known factors, and the second part is covering all the unknown at the high level. So this can help us in different ways. The first is obviously the automated annotation. We run it for some small batch of samples with known information available and train the model, and then we actually fit it or like check the model's performance on like real observations or unannotated observations for which we don't have the labels, and you can actually use these methods for those kind of automated annotation, also to see like different structure of the unknown unknowns, because many times the scientists know the part they know, but also there is a lot of big chunk of like unknown factors that they want to investigate about. This approach actually gives us the latent space that are actually independent of your known factors, so you can actually pinpoint or focus more only on the unknown factors a little bit better. Thirdly, the third point is basically the importance of the existing partial information. Many times when I talk with the domain scientists, they say that, okay, I have this data and I have this partial information. They should be important to the data, but we are not sure, and we are not sure they are that much relevant or not. For that, we can actually utilize it in this format and see like uh, if I use those things or those candidate known information in the ZOX, then how the sensitivity of the Z reconstruction, the unknown factors are actually increasing or decreasing, right? If we actually kind of pinpoint most of the important factors in the ZOX part, then the importance of the Z reconstruction would be not much, right? So if we perturb the Z reconstruction, we will probably not see that much perturbation in the generated images, and that can tell us that the known information that you have, they're like exhaustive enough. They are actually representing all the important ground truth variability. So using this kind of disentangled approach, we can also check the importance of existing candidate partial information that are available to the domain scientist. Um, we're still working on it, and we are actually extending it in different scientific applications. And if you have any suggestion or if you have any kind of potential usage for this kind of application, please let us know. And with that, I'll probably stop and answer if there is any question.
Great. All right. Thanks, Arka. Yeah, we're running a little bit short on time, but if anybody has a quick question, that would be swell. I will take presenters' prerogative just for a moment and ask just briefly, can you give us just any sense of what kind of compute resources you're using on the back end for this?
Basically, yeah, it's a little bit, it depends on the data set, right? So for the galaxy simulation, there was like 1600 images with 101 like dimension. So for that, mostly for this kind of training, I am using Argonne's supercomputers like ALCF or LCRC allocations for running these things. But they are not that different from running a standard VAE or standard diffusion. It's not computationally that much different from running a standard generative models. So yeah, if people are actually using their own laptop or their computer like high performance clusters, similar thing can be done here. We are not adding any computational burden excessively by enforcing the disentanglement.
Great. All right, I think just because we're basically out of time here, I think we better wrap up. I will say that our email is on the screen here. If you've got questions, you can that'll be in the recording as well. So I would like to thank again Arka for the awesome talk. Thanks for everyone for attending Lake Tech Talk series today. Next Tech Talk is December 11th, 2025. Carrie Holt of Los Comas Observatory will be joining us to present FOMO, or fear of missing out, which is like that's the pun anyway. It's a Rubin-Falov observation framework. So really looking forward to that. In the interim, please join the LSST Discovery Alliance hashtag link Tech Talk Slack channel. Link at lists.lsst.org mailing list for information and future announcements. There's also much more information, including links in the Rubin Community Forum and the calendar at the LSST Discovery Alliance website. Link Frameworks holds office hours every Thursday at 10 a.m., except for when they conflict with this talk. If you have an idea for a tech talk, we would love to hear from you. Please send us a message via LSST Discovery Alliance Slack or via email, which are both listed on the Tech Talk webpage. Again, we'll post this up on YouTube when we get a chance in the next week or so. And then we thank everybody again for joining us. Have a great rest of your day or night. Thank you very much.
Thanks, everyone.